Good afternoon, students. So in the last video lecture we were discussing about linear vector space, and in linear vector space the operators will exist. These operators will carry out the linear operation. So the operators must be linear operators. The transformation must be linear. The transformation from one system to another system in the linear vector space must be linear. So this is what we discussed. So those operations are nothing but differentiation, squaring, integration, multiplication, and all those things. Even differentiation of second order, third order, all those things will come under operations. So some operator will operate on the wave function. Wave function in the sense, in quantum mechanics we know that all small particles, quantum particles, will be represented in terms of waves. So there must be a wave function which represents the quantum particle. So an operator which will operate on the wave function will give some eigenvalue with the wave function that we are going to discuss later. Okay. So the linear operation means linear operators must be there. So the operation must be linear. The two conditions should be satisfied. So these two conditions should be satisfied, that we know that the linear operation in linear vector space. These two conditions. One is the addition, another one is scalar multiplication. So these two conditions should be satisfied. So this is the addition, the rule for the addition, and this is for the scalar multiplication. These two conditions should be satisfied for the linear operation, for the linear transformation. The operator operates on the combined system. The wave function is a combined system. That will give you the operator operates on the individual system. See, this is your combined system. This is your individual system. So the operator operates on the combined system will give you the operator operates on the individual system. For all your wave functions, psi1, psi2, psi3, dot dot dot, everything should belong to linear vector space, vector space. And the second one is operator operates on the scalar multiplication, operates on one constant, some constant. With the wave function will give you C operator operates on psi. That C belongs to your real space, or it can be even complex number. So this is what we discussed in the last class. So linear operator means the operator operates on the combined system will give you operator operates on the individual system. So you have to remember this one. So an operator O is a linear operator. O, the small cap is there. That's called the operator. See, I have written as a O to represent an operator. O, small cap I have written. So this is called an operator. Suppose we want to write an operator A. So A, one small cap. See, this is a cap. Okay, O. So O operator is a linear operator. If any arbitrary function psi1 of x and psi2 of x with the following two conditions. One is the addition, another one is scalar multiplication. In quantum mechanics, which we are going to see in the next semester, the observables are nothing but position, momentum, angular momentum, energy. If you have an entity which depends on position and momentum, what we call this an observable. All observables are associated with the operators. In quantum mechanics, the position is associated with the operator. It's an observable. For example, when you take readings in the lab, we are going to take the readings. For any experiment, we will take some readings, 6 readings or 7 readings. So here also position is exactly like a reading. So position is an observable. Observable is associated with the operator. For example, when you take position, usually position is represented in terms of x. So what is an operator? X cap. Momentum is represented as P. How? P cap, that's all. So this is an operator. Okay, angular momentum L. So L cap. And energy E cap. So E is an observable which is associated with the operator. And many others are represented by linear operators. So they are all linear operators. Linear transformation, just now I said the linear transformation should be there in vector space. The linear transformation, the condition for linear transformation is this one. T stands for linear transformation. Linear transformation of any vector will give you some other vector. That vector will be always in vector space. So this is the condition. From a vector space into itself is called a linear operator. So if this condition, these two conditions are satisfied, then we say that operators are linear. The transformation nothing but linear transformation. Is it okay? So for any operator we can write the following equation. Just now I said the operator operates on wave function. Wave function will give you, listen to me, it's very important one. Operator operates on the wave function will give you eigenvalue O, eigenvalue, okay, value with the operator. I repeat, this is very important one. This is called eigenvalue equation, which says that in quantum mechanics, this is very famous equation. The quantum mechanics starts from eigenvalue equation. Okay, operator operates on the function, wave function will give you value, simply it's a value with the wave function. Suppose if these two wave functions are the same, psi equals psi, here also psi you have and that side also you have psi. What we call this as eigen function. If both the wave functions are same, we call this as eigen functions. Suppose if they are not same, they are different, then we say that they are simply wave function, simply function. Is it okay? Eigen function is different from function. If they are same, here it is same, so psi is termed as eigen function. Instead of suppose if you get phi, for example, you just take an operator d by dx. You just take an operator d by dx, e power 2x. Okay, e power 2x, which is equal to, you are going to differentiate e power 2x. What is the value? 2 e power 2x. 2 is the eigenvalue. E power 2x is eigen function. Very good. Is it okay? Suppose d by dx of x squared. D by dx of x squared. What is the value? 2x. 2 is the eigenvalue. What about x? Here you have differentiated x squared. You have obtained only x. So it is not an eigen function. It is simply, it's a function. Is it okay? So here psi is a eigen function and this equation is known as eigenvalue equation. If the same wave function is obtained, that function is known as eigen function. This equation is known as eigenvalue equation. Any doubt? The mathematical operators such as differentiation, integration, addition, subtraction, squaring also is an operator. Okay, it's an operation. So squaring and so are operators. It is defined as the rule by which a different function is obtained when an operator operates on any given function. See, this can also be done. For example, just now I said d by dx of x squared, which will give you as 2x. D by dx of x squared will give you 2x. See, it's a different function. Okay, here it's the same. D by dx of e power x. The answer will be 1 into e power x. 1 is the eigenvalue. But here it is different. But both are linear operators. The operation is linear. But here it is eigen function. Here it is simply function. Is it okay? Now we have given some examples for linear operation. So if an operator is a differentiate operator, then the function. For example, differentiation of f of x equal to g of x. Differentiation of x squared equal to 2x. So d by dx is an operator. D by dx is an operator. X squared is a function, wave function. It's a function. After differentiating, you will get 2x. 2 stands for eigenvalue. Eigen means proper. So eigen is a Latin word. It means proper value. So eigenvalue. X stands for simply wave function. Now we will go for this one. D by dx of psi 1 plus psi 2. Operator operates on the combined system. See, psi 1 plus psi 2 is a combined system, which is equal to operator operates on the individual system. So it must be a linear function, linear transformation. It's very clear that it's a linear one. Is it okay? Now, not only in these things, vector space, but also in matrices also it will work out. As I said earlier, vectors are represented in terms of matrices. We discussed earlier. So not only in vectors, but also in matrix also work out. For example, y equals ax. A is an operator, it's a matrix. You are going to multiply with x, you will get another matrix y. So it's a linear operation. A, you have a matrix, you are going to multiply with matrix multiplication with x, you will get y. So it's a linear operation in terms of matrices. So for example, you have 2 by 2 matrix and multiplied by c by d, that will give you answer as a b. So matrix multiplication is a linear operation. Is it okay? Now, these things are not linear. For example, squaring is not linear. But when you take, first we will take f of x equals sin x. And what's the rule that we have learned? Operator operates on the combined section. Just go for sin x plus x1 plus x2, which is not equal to sin x1 plus sin x2. It's very clear. So sin pi by 2 plus pi by 3 is different from sin pi by 2 if we calculate plus sin pi by 3. This will have a different value, this will have different value. Combined together, this will have different value. If you are going to add these two, surely it will not be equal. It is not a linear function. Okay, squaring. What about squaring? F of x equals x square. See, for any linear operation, this rule should be obeyed. You just see here, rules are different. Okay, so it is not. So f of x equals sin x is not a linear transformation. Now we will go for the second problem. F of x equals x square. You have x plus x1 plus x2 whole square, which is not equal to x1 square plus x2 square. For example, we take 1 plus 2. 1 for x1, 2 for x2. So 1 plus 2 whole square is not equal to 1 square plus 2 square. So we can say that f of x equals x squared is not a linear transformation. We should not judge that always this will be a linear function. So here they are not linear. Squaring, taking the square root, and when you go for any trigonometric function, they are not linear transformation, linear functions. Is it okay? Now problem 1. So we are going to see one problem which obeys addition and scalar multiplication. So whether this function is linear or not, we are going to check. Okay, problem 1. So we are going to verify a linear transformation t from r squared into r squared. So we are going to take only 2 components. R squared stands for 2 components. R cube stands for 3 components, real space. R stands for single component. You have already 1D, 2D, 3D. So now we have taken only R squared. It means real space 2 dimension, x and y, or v1, v2, or u1, u2. So now T stands for linear transformation. Linear transformation of v1, v2 is given as this condition. It's given. Already it is in the problem. We are going to check whether this one is linear transformation or not. We are going to check. That's all. Okay. So first we will go for addition. Second, after that we will go for scalar multiplication. So we know that we just will have u vector as we are going to keep as u1, u2. V vector as v1, v2. So in r square, we are going to just keep. Vector addition. Vector addition, we know that u plus v is given as u plus v is given as u1. Adding the vectors, nothing but adding the components. So you have to add the components. These are all components of a vector. These are all components of a vector. 2 components exist because this is r square. Okay, suppose if there are 3 components, you will have u1, u2, u3. That's all. So you have now, we are going to add u plus v. So this is your u, this is your v. So this becomes u1 plus v1, u2 plus v2. Any doubt? U plus v? U plus v, just adding the components. We are going to add the components. u1 plus v1, u1 plus v1, u2 plus v2. Now the linear transformation of addition of t, u plus v combined system will give you t of, what is u plus v? u1 plus v1, u2 plus v2. So u1 plus v1, u2 plus v2. Any doubt? We are going to take this as v1 and we are going to take this as v2. Now what is this operation? This operation will do u1 plus v1 according to this rule. What is v1? v1 is this one. What is v2? What is, see, minus V2 is given. What is V2? U2 plus V2. So first I am going to write V1 here. Minus. V2 is here. Minus. So minus, instead of V2, U2 plus V2. Comma. Here V1 is here. What is V1? U1 plus V1. Then after that plus 2V2. So plus 2V2. Any doubt? Very simple one. Is it okay? Now, U1 minus U2, you combine together. Similarly, V1 minus V2. We are going to add these two. Comma, U1 plus 2U2, V1 plus 2V2. Is it okay? I repeat, U1 and here U2 is here. So U1 minus U2, minus U2. And here V1, I have written V1, here minus V2, comma, U1, 2U2. So 2U2 is here. Then V1 plus 2V2. Is it okay? So U1 minus U2, I can write this as taking U components alone. So U1 minus U2, U1 plus 2U2. I have taken only U components alone. I have taken V components here. So V1 minus V2, comma V1 plus 2V2. What is this one? What is this one? You just say, what immediately you can say that this is nothing but V. What is this one? This is nothing but your U. See, what is U? U is given as U1 minus U2 plus, comma, U1 plus 2U2. What is V? V is nothing but V1 minus V2, comma, V1 plus 2V2. So this is termed as U and this is termed as V. So transformation of U, here linear transformation of V. What is on the left hand side? Transformation of U plus V. What is right hand side? Transformation of U plus V. This is combined system, this is individual system. So we can say that the transformation, linear transformation of the combined system is equal to linear transformation of individual system. So addition is proved. Any doubt on the slide? It's very simple one. On the slide. So now we'll go for the multiplication. So we are going to prove this one. We are going to prove T of Cu which is equal to, one bracket should be there, okay? One bracket should be there. T of Cu which is equal to Ctu. We are going to prove this one. So Cu equals, we are going to consider Cu equals Cu1 comma U2 which is equal to Cu1 comma Cu2. Now transformation of, linear transformation of Cu is given by transformation of Cu1 comma Cu2. We are going to keep this as V1, we are going to keep this V2 and we are going to use this one. So this becomes V1. See, this is your V1, this is your minus V2 comma V1 plus 2V2 according to the problem that we will have to satisfy. Okay, so Cu1 minus Cu2 comma Cu1 plus 2Cu2. I can pull C out, it's a scalar, I can pull out. So C which is equal to U1 minus U2, C1 U1 plus 2U2. What is this one? This is nothing but Tu. So this is nothing but, here it is V, here it is U. We have taken as U here. So T Cu which will give you C Tu. So this is what the scalar multiplication is. Any doubt? Therefore T is a linear transformation because it obeys the condition which it has to satisfy. That is, one is addition, second one is scalar multiplication. So they are all, T is a linear operation, linear operator. Linear transformation is going on. Now we will go for problem 2. Problem 2 is in 3 dimensions. So we are going to take the transformation, linear transformation with R cube. We are going to have some operation and that will give you R cube which belongs to the same vector space. So we are going to check whether it is a linear transformation or not. We are going to check. Now T of 1 comma 0 comma 0 is given. So these are all given data. It is given as T of 1 0 0 is given as 2 minus 1 4. T of 0 1 0 is given as 1 5 minus 2. T of 0 0 1 is given as 0 3 1. So they are all conditions. We are going to find out T of 2 3 minus 2. We are going to find out T 2 3 minus 2. So 2 3 minus 2 can be written as 2 1 0 plus 3 0 1 0, correct, minus 2 0 0 1. Now the linear transformation of on both sides. So linear transformation means you are going to write t of 2 3 minus 2, 2t of this one, 3t of this one, minus 2t of this one, where t is the linear transformation. What is t of 1 0 0? T of 1 0 is given as 2 minus 1 4. So you can write 2 minus 1 4. What is t of 0 1 0? 1 5 minus 2. What is t of 0 0 1? It is given as this. So 2 multiplied by this. Okay. This one 3 multiplied by this. You will have to add all the components now. Similarly, minus 2 multiplied by this, you will have to add all the components. We will add the first component. 2 2s are 4. 3 1s are 3. So 3 plus 2. Come on. 2 2s are 4. 4 plus 3. So it is 7. Minus 2 multiplied by 0, 0. So it's 7. Any doubt? We'll go for the second one. So this must be minus 2. This must be 15. 15 minus 2 is 13. Here it is minus 6. So 13 minus 6 is 7. See, 7 is here. Any doubt? 7. Similarly, you can go for the last one. 2 multiplied by 4, 8. 3 multiplied by minus 2. Minus 6. So 8 minus 6, it will be 2. 2, then we have minus 2. Answer is 0. 0. See, 0, 0. So the transformation, linear transformation of one system is equal to another system. That system also exists in vector space. So it obeys. So it's a linear operation. Okay, any doubt? Not only, as I said, not only in vectors, but also it obeys in matrices too. So for example, you have T in matrices. We have R squared, which gives R3. See here, we have the linear transformation of R squared. Okay, 2 coordinates will give you now 3 coordinates. Answer is 3 coordinates. We are going to look into. So it is defined as T of V, which is equal to AV. So A vector is given as this one and V vector is given as this. We are going to find out T of V, where V is 2 comma minus 1. So apply this one. You have AV. This is your A. So V is given as 2 minus 1. So 2 minus 1. You just have the matrix multiplication. Matrix multiplication will give you 6 3 0. This is in the column vector. You can write it in the row vector. So T of 2 comma minus 1 is given as 6 3 0. 2 comma minus 1. Only 2 components exist. R squared. 6 3 0. 3 components exist. See, R cube. So the transformation of R squared, which will give you R cube. So this also is a linear transformation. Okay. So R squared, this is R squared, this is your R cube vector. Okay. Now we have come to the next title, which is nothing but Dirac notation. Already we learned Dirac notation earlier. In the last video lecture, we learnt about Dirac notation earlier. So as I said earlier, Paul Dirac from UK introduced Ket-Bra notation. Okay, Paul Dirac. Okay, Ket-Bra notation. So this is called Dirac notation. We already learnt. Ket vectors are represented as column vectors. Okay, Bra vectors are represented as row vectors. When you are going to multiply these two, Bra with Ket, what will be the answer? Scalar. Okay, it's a scalar product. It's a scalar product or inner product. The answer will be a number. Okay. For example, if it is equal to 0, these two scalars must be orthogonal to each other. Very good. Perpendicular to each other. Suppose the answer is 1, it is normalized. So orthonormal. If it is normalized as well orthogonal, orthonormalized. We usually will consider like this. Okay. Suppose if it is Ket with Bra. Earlier we said Bra with Ket. Now we are going to have the operation as Ket with Bra. So it's a vector quantity. Vector quantity. So you will have only matrices. So these notations are introduced by Paul Dirac. So what we call this as Dirac notations. Dirac notation. It will be very, very easier to write. So that's the reason that he has introduced. The physical state of a system is represented in quantum mechanics by elements of a Gilbert space. As I said, n-dimensional space is nothing but a Gilbert space. Quantum mechanics lives in Gilbert space. Quantum mechanics. So Gilbert space, these elements are called state vectors. For example, when you are going to represent any quantum system, for example, electron, you have an electron, it's a quantum system. This is represented in terms of a state vector. See, earlier we said psi. Can you remember psi? Just now we have discussed about psi 1 and psi 2. Psi 1 is an electron, one electron. Psi 2 is another electron. Psi 1 can be represented in terms of, for example, proton. Psi 2 is another proton. For example, they are all quantum systems. So they are called as state vectors. So psi 1, psi 2 are functions of position and time. So what we call this as a state vector. It's a new term, state vector. The state vectors in different bases by means of function expansions. So this is what I said, it's a function. Psi is a function of x comma t. This is analogous to specify an ordinary Euclidean vector by its components in various coordinate systems. The meaning of the vector is of course independent of the coordinate system chosen to represent its components. So they are all linearly independent vectors. Psi 1, psi 2, psi 3, they are all linearly independent vectors. Okay, so kets, we know kets are represented in terms of this notation. So you have a line and you have a greater than symbol in which you have an element. Okay, so this element is nothing but a state vector in quantum mechanics, but here it's a function. So Dirac denoted the state vector psi by the symbol, this symbol, which he called as a ket vector. So this is nothing but your ket vector, or simply a ket. Kets belong to a Gilbert space, or in a short to the ket space. So ket space. Okay, it's nothing but a Gilbert space. We call this as ket space. Similarly, bra space. We know from linear algebra that a dual space is associated with every vector space. So whenever there exists a normal vector, this is called a normal vector, and we can take the complex conjugate of this vector. For all ket vectors, there will be bra vectors. So they are all conjugate. So they are all conjugate to each other. For example, you have a ket vector. The complex conjugate of ket vectors is nothing but bra vectors. The complex conjugate of bra vectors is nothing but ket vectors. So there must be a dual space. For example, in linear vector space, if we have a collection of all normal wave functions, for which we can have the corresponding complex numbers in dual space. So what we call this as dual space. So Dirac denoted the elements of a dual space by the symbol bra. So this is your bra, which he called as a bra vector, or simply by a bra. Again, while kets belong to the Gilbert space, the corresponding bras also will belong to dual space. Ket and bra, they live in Gilbert space, what we call this vector space. Quantum mechanics lives in vector space. That's all. Okay. So bra and ket. So Dirac notation for the inner product. So we know that about inner product. This is denoted in some of the books. You may find inner product is like this, with this symbol, phi comma psi. Phi means normal vector. See, psi is a normal vector. Phi is the complex conjugate. So this is your ket, this is your bra. Okay. So psi is a normal wave function, and phi is nothing but complex conjugate. See, look over here. You have, see, phi star. It means complex conjugate. You have taken complex conjugate. See, complex conjugate. Psi is as it is. And from minus into plus infinity, which comes under in d tau. D tau stands for dx, dy, dz, which is nothing but d cube r. D cube r is nothing but dx, dy, dz. In some other book, you may find d tau. Okay. The norm is real and positive. We know already. For any vector, the norm psi is a real and positive.